We now turn our attention to the last section for epidemiology, questions regarding research study designs. If history is any guide at all, the question is not, will I have any questions on research study designs? You almost certainly will. These are very common. The real question is, how many will you have? And frankly, although I can never give an exact number, certainly up to 4, 3, 2, something in that range are almost certain. These are questions you should, again, feel good about, feel comfortable with. Let's understand why they seem to test you in research study designs. They don't really expect that you're going to be a researcher, but they do expect you're going to be a consumer of research. And so most of the questions are oriented towards your ability to understand what's being presented, and your ability to understand whether something was done correctly or whether an error was made. I'm not only going to tell you there's questions of research study designs, I'm going to go one step further. I'm going to tell you exactly what the questions are. They're going to give you a long paragraph, data presented, and then they're going to ask you one of the following 4 questions. They're going to ask you, 1, what type of bias, if any, is in this research study? They're going to ask you, 2, how would you fix this bias? Sometimes hidden in the question, if this research were repeated, what would be done differently or should be done differently the next time? 3, what type of study design do you call this? What's the label you use to describe the study design? Or 4, how would you analyze data from the study design? What would you do with the data in order to get a sense of whether the results we have matter or don't matter? Those are the questions, folks. When they show up on your exam, you can't possibly be surprised. Those questions are easy to anticipate. And so what we have to do now is just prepare you to answer those questions when they show up. That means we're going to start by talking about bias. Bias is deviation from truth. The whole point about research is to remove us from the limitations of our subjective life experience into the realm of, well, more objective, more confident sense of what reality looks like. And when research doesn't do that, when research leads us astray, we say it's biased. Now there's 2 ways we look for bias: reliability and validity. Reliability is really consistency. Same result every time. There's another synonym you're going to see, precision, but most people tell me that consistency has much more intuitive appeal. If I give you a test today to see how well you're going to do in your Step 1 exam, and you get 80% of the questions right, nice score. If I give you a test tomorrow, see how you're going to do on the exam, and you get 30% correct, not a good score, aren't you bothered by the difference in those? Well, that's a problem with reliability. There's an inconsistency in the results. Validity, by contrast, is accuracy. Did you measure what you say you measured? Did you measure what you want to measure? If there's a target, did you hit the target? If I want to see how tall you are, and I bring in a bathroom scale, and I have you step on the scale, and I read what the scale says, does that sound like a good way to measure how tall you are? No, it's not a problem with reliability. The scale may give you the same number every time. It's a problem with validity. I'm not measuring what it is I say I want to measure. I say I want to measure height, but in fact I'm measuring weight. Reliability is consistency. Validity is accuracy. Did you hit what you were aiming at? Make sure these concepts are relatively clear. I'm going to fall back with a familiar, for at least some of you, 2-target example. I'm going to take some shots at the target on the left. Here's my shots. All right, that's my shooting. What do you think? Good shooting? Well, the shots are at least nicely, tightly clustered, yes? But I missed the target altogether. So what you have here is good reliability, consistency, but no real validity. The shots are consistent, they're all clustered, but I missed the target. As compared to this presentation on the right, there's the shots once again. Now I have the shots clustered, still reliable, but now I've hit the bullseye of the target, and so I'm also valid. On the left, reliability yes, validity no. On the right, reliability yes and validity yes. Now please note, despite what you might see in other contexts, it's impossible to have validity without having reliability. You have to first cluster your shots before you can cluster them in the bullseye. So, if I tell you a test is reliable, you know nothing about validity. If I tell you a test is valid, you know it's also, by implication, reliable, because I wouldn't have validity unless you had the reliability in the first place. In the language of logic, we say reliability is a necessary but not sufficient condition for validity. It has to be there, but something else has to be there for validity to be in place. Reliability is consistency. Are you getting the same result every time? Validity is accuracy, hitting the bullseye, a pictorial example which you have here on the right. Good. With those concepts out of the way, we're now going to walk through being able to identify and then be able to come up with solutions for different kinds of bias. Now, before I go through the content, a little orienting comment here. Over the years as I've been teaching this content, I've noticed students are pretty good at reading what's in the syllabus and then telling me back what's in the syllabus. But that doesn't prepare you to answer the question on the exam. Because the question on the exam will not say, tell me about this kind of bias. Instead, anticipate. The question you're going to see is going to provide a paragraph where there is some bias and then ask you what kind of bias you're looking at. In short, the mental headset here is the same headset you should have in pathology. We're not going to ask you to describe the disease. We're going to give you an example of it and then have you label what the pathology is. In this case, label what kind of bias you have here. And so your mental process in answering these questions is really as important as your memorization of the details. And the mental process I suggest is as follows. You're first going to read the paragraph, and usually something in your gut says, wait a minute, something's wrong here. Something's not right. And then you say, ah, this is what's not right, and you can talk to yourself about it as a sentence. And then and only then do you say, we call this blank, and you come up with the name of the bias. Let's do that sequence again. Something's wrong, this is what's wrong, and here's what we call it. And I ask you to notice, isn't it how you do medical diagnosis? Patient walks in, you go, whoa, something's not right here. Then you say, well, here's the symptoms, and then you say, ah, and that together it's exactly the same headset you're doing for diagnosis. We're just diagnosing bias instead of diagnosing pathology here. You have to know, I want to outline in the beginning here, the types of bias, but also the solutions. I remind you again, the same way when you're diagnosing, you got to not only know what's wrong with the patient, but you ought to have at least a preliminary sense of how to treat that. I want you to think about the same issue here. They may not ask you what type of bias it is. They may simply say, if this study were repeated, what should be done differently? In order to get to that answer, you're going to have to correctly assess the bias and then know what is the solution for the bias. We're going to now talk our way through different types of bias, trying to give you examples so you'll know them when you see them, and then trying to get you to realize what's the reasonable solution to deal with that bias when it occurs. We begin, where we should, with selection bias, also known in many circles as sampling bias. The issue here is fairly straightforward. The people that are in your study are not a good representation of the people outside your study. And so the point of research is not simply to look at the people in your study, but it's to generalize from your study to the rest of the world. Well, if the people in are not a match of the people who's out, that generalization becomes, at the very least, problematic. Selection bias is when the people in are not a good template for estimating all the other general population of the people that are not in your study. Often, we see this in research as a result of the so-called convenience sample. Convenience sample where you're just looking at the people that are available to you, assessing data from them. But there's an obvious question remaining. Are the people that you're assessing really a good representation you can generalize from? You can always say something about the people in your study, but can you say something about the general community based on what's in your study? Try to give you an example to make this painfully clear. Suppose I want to do a study getting a sense of the cardiovascular fitness of people that live in Manhattan. To do that, I hire my staff, about 10 very dedicated researchers. I train them, and I give them some measurement paraphernalia, and I set them outside of 10 local health clubs in Manhattan. Over a 2-week period, they stop and measure blood pressure and other physiological parameters of everyone that comes in and out of the health club. And then they bring that data back to me. With that data in hand, I'm now going to estimate the cardiovascular fitness of people that live in New York. What do you think? Good study? Well, of course, it's a terrible study, because people going in and out of health clubs are not representative of the general population. And so the conclusion I reached, based on the people coming out of health clubs, would not tell me anything about the general population of New York. Now, go back over and let me do the thought process with you. I said we're going to take people, set them outside of 10 local health clubs in this example, and have them measure parameters, physiological parameters, people going in and out of the health club. As you heard me, you should say, wait a minute, that doesn't make any sense. And then you're going to say, that doesn't make any sense because people who go to health clubs are not just like the general population. And finally, you're going to say, we call that sampling bias. That's a convenient sample. Once again, just to review the process, something's wrong, here's what's wrong, here's what we call it. But there's a number of kinds of sampling bias. So let's walk through some other examples. When I was down in the city of Houston many years ago, I was able, after great effort, to negotiate to get all the hospitals in the Houston area to give me access to their hospital discharge records. Using that information, I looked at diagnoses related to and treatments associated with tuberculosis. And using that information and a fairly complex formula, I derived an estimate of the prevalence of TB in the Houston metropolitan area. Now, question, did I get a good estimate or a poor estimate of TB in Houston? Well, the answer, of course, is I got a terrible estimate. Using hospital data to reflect population disease is a stupid idea. Because that would only make sense if the people that come into the hospital are in some sense a random representation of people in the general community, which we know for a variety of reasons is not the case. Measuring what's in the general population by what comes into the hospital is a dangerous and usually a really ludicrous idea. And that said, you're going to hear this all the time. I just read in the newspaper a couple months ago that in Chicago, where I'm from, we're beating cocaine. That cocaine usage is on its way down. And the evidence presented in the article to demonstrate that was they showed a chart that showed that over the last 5 years, the number of cases of cocaine-related overdoses at the local county hospital has gone down each of the 5 years. Well, come on, you ought to be laughing at this because just because fewer people are coming with cocaine-related overdoses doesn't mean anything at all about cocaine usage in the community. In fact, it's possible cocaine usage has gone up and people have just learned to use the cocaine better so they don't come into the hospital as much. Using hospital data to get a sense of population parameters is a really, really bad idea. In fact, it's so bad, it has a name. We call this Bergson's bias. Using medical records to estimate population parameters is a bad idea. One final idea here, non-respondent bias. Non-respondent bias is also known as the volunteer effect. The volunteer effect is only a problem when we have volunteer subjects. If there are no volunteer subjects, we don't have any problem here. Oh, by the way, give this a moment's thought. When do we have volunteer subjects in medical research? Right, always. They're not allowed to be in your study unless they volunteered. And so I just told you this is always a problem. The people, when approached, who decide to agree to be in your study, and the people when approached who decide to not be in your study, well, if we assume that's not a random choice, it's likely the people that agree to participate and the people who agree not to participate are two very different kinds of people, right? And so if we reach conclusions about the general population based on only people who volunteer, there's a great danger that we're not adequately representing the population as a whole. We're biased towards that subgroup that come in to be in the study. Ask yourself, who signs up for these long-term longitudinal studies you read about in the newspaper? Well, somebody once said the same people show up for jury duty. And you know what a representative sample that isn't of the population, right? The people that come in are not a good representation of the general population. A lot of medical research, some people would argue most medical knowledge, is built atop a huge sampling bias. I have a colleague who's fond of pointing out that most medical knowledge is based on white rats and white males. Although that's a little bit overstated, there is some grain of truth in that. Because only, maybe in the last 8 to 10 years, we've been making great efforts to make sure women and non-whites are enrolled in medical studies. And you know, we've discovered something. We've discovered that what's true for white males is not necessarily true for women. Because, I don't know if you knew this, apparently men and women are different. I don't know if you knew that. And so what we decide for one gender is not true for the other gender. And we've discovered that what's true for white males is not true for any other males in the known universe. Hispanic, Asian, African American, Southern Asian subcontinent. You can't look at white males and decide what's true for everybody else. Only looking at one group of the population is a selection bias problem. It's a non-respondent bias problem. Now, you can see that the selection bias can really screw up your ability to get a clear picture about what's happening in the world around you. So we need a solution to this. And the solution we have to sampling bias is a random independent sample. A random independent sample simply says we must be able to go out in the population and randomly bring in people, and because of that random process, we're going to have a good representation of the people that are out there. This makes who's out match who's in. That's the first step of the process, but it's only the first step. Why? Because no matter how hard you try, you'll never be perfect. The ability to get a perfect random sample is pretty much zero. Nonetheless, we make an effort. Once we make the effort, we then look at characteristics of the population, look at characteristics of people in the study, and see if they match. If they do, then we feel pretty happy about the sample we have. If they don't, then we have to do some other correction. Let me be concrete. Suppose I happen to know from census data that in this community where I'm doing research, half the people are white and half are African American. I now go and try to get a good sample out of the community, and I discover when I look at my data that in my sample, 70% are white and 30% are African American. We have a problem here. I don't have a nice match to what's outside there. The next thing I'm going to do is roll up my sleeves and go out and try to get more African Americans into my study. I work hard, I recruit more, I go door to door, and then with great effort, now I have 60% white and 40% African American. Better, but I haven't brought it home yet. To bring it all the way home, we're going to do one final thing. We're going to weight the data when we do analysis. In short, I'm going to treat the 60% white as if it's 50% white, and I'm going to treat the 40% African American as if it's 50%. If this reminds you of the kind of thing we talked about when we talked about adjusted rates, the process is essentially parallel. It's not the same, but it's essentially a parallel process, and therefore enables us to get the data so it does in fact match the general population. What's the solution to sampling bias, selection bias? First, a random independent sample, and then weight the data to make sure it matches the general population. Sampling bias, selection bias, the people in the study are not a good representation. It's not a match to the people out in the general community. If the sample's okay, we next worry about measurement bias. Measurement bias, the way I get information from the sample distorts the information that I get. Now, sometimes measurement bias is straightforward and easy to see. Other times, it's more subtle. Let's try the straightforward example. Let's say I'm doing a survey trying to find out how people feel about their primary care physician. I walk up to someone in the street, they agree to be part of my survey, and I ask them my questions. Question 1, you'd like your physician, don't you, I ask? And they say, yes, I do. Good. I say, you think your physician's wonderful, don't you? And they say, yes, I do. And then I say, please look, you think your physician should make a lot more money, a great deal more money, or a ton more money? Please pick one. And they say a ton more money. I say, thank you very much. And now I've collected good data. No, I've collected terrible data. Those were, I hope you recognize them, leading questions, suggesting in nonverbal, word choice, tone, what the answer should be. You learn nothing whatsoever about that person's actual opinion. What you learned about was my bias in asking the question. Those kind of leading questions, we coach you to avoid these all the time in clinical situations, are a measurement bias problem. More concerning is the more subtle issue, the so-called Hawthorne effect. The Hawthorne effect was discovered of all places in Chicago, where I'm from. Back in the 1920s and 30s, some bright young researchers knocked at the door of a plant manager, a man who ran a factory called the Hawthorne Western Electric Plant on the west side of the city. They said to the manager, let us do research at your factory and we'll tell you how to make people more productive. More productive. Let me translate that for you. They'll work harder for less money. The guy that ran the factory said, come on in, that sounds good to me. And he gave them a room off to the side of the factory where they could tinker and see what would make people more productive. Well, the first thing they decided to focus on was something simple, illumination. Gradually, day by day, incrementally, they increased the wattage in the room. So the room got brighter and brighter and brighter, up to, by one account, the brightest noonday sun. Then they looked at production records, and what did they find? As the room got brighter and brighter and brighter, productivity got correspondingly higher and higher and higher. Wow, they said, we're on to something. Make the room as bright as possible, you get more work out of people. Good idea. Well, they were at least moderately good researchers, so before they published that, they tried on one other thing. They reversed the process. Again, they went in where people were doing the work, and this time they reduced the wattage in the room day by day. So incrementally, subtly, every day, the room got dimmer and dimmer and dimmer, down by one account to about the level of moonlight. And then they looked at production records. What did they find? As the room got dimmer and dimmer and dimmer, productivity went higher and higher and higher. Oops. Clearly, we have a problem here, because when the lighting gets greater, productivity goes up. When the lighting gets dimmer, productivity goes up. Clearly, the logic tells us it's not the lighting. What is it? Well, if you're ever trying to detect bias in a research study, I have a strong suggestion for you. Put yourself physically, if you can, or mentally, if you can, in the position of the research subjects. Look around you and think about what they might be responding to. So, think about, let's say, the 5 people in the front here. You're all doing assembly work at this factory. You're doing assembly work for which you're getting paid. And now, for reasons that may not be clear to you, one day some young white males wearing long white lab coats carrying clipboards start to walk around, watch you, and take detailed notes on your behavior. What effect might this have on that behavior? Of course. What's the Hawthorne effect? Simply put, the fact of observation by itself changes what's observed. The act of observation is all that it takes to change the thing that's observed. Now, some of you should think about and remember this as nothing more than the social science variant of the old Heisenberg uncertainty principle. Remember this? Measuring the electron changes the electron, measuring you changes you. We have a real problem here, because to do research, I need to measure. But if measurement changes by the very fact of measurement, how are we ever going to get a picture of what reality looks like? Well, the solution to this type of bias is have a control group. See, the control group gets measured just like the intervention group gets measured. So both groups might be changed by the measurement, okay, but if I find differences between the two groups, since measurement is a constant, the differences I find can't be due to the measurement. The reason why we have control groups is to rule out the Hawthorne effect. Making measurement a constant, any difference I see can't be due to that measurement. The solution to measurement bias is have the control group. If measurement's okay, the next thing we're going to worry about is experimenter expectancy effect, sometimes simply called the expectancy effect. Experimenter expectancy effect is discovered and demonstrated in a now classic study. See, the issue here is what the research expects or thinks they're going to find is usually what they actually do find. And we demonstrate this by going into a grade school class at the very beginning of the school year. And we give all the students in the class a test. Now, folks, so you're clear, the test is bogus. It measures nothing. But we tell the teacher, based on these test results, this side of the class over here on my right, these are the bright students. Wow, really high potential. And this side of the class over here on my left, they're just average. And then, doing nothing more, we walk away. We come back at the end of the school year and we pull the grades. You know how this ends. Who has all the good grades? The high potential side of the class has all the good grades, right? And now, here's the kicker. Now we're going to get an objective-based competency test. A test that assesses not the teacher's opinion, but objectively what the students actually learned. Any difference between the two sides of the class? Absolutely yes. The high potential students got the better grades and did better on the objective test. Understand, experiment expectancy works not at the level of evaluation, but it works at the level of interaction. Let's think about this. The teacher was told these are the high potential students. And so if you watched her over the course of time, you'd have seen that in the year she spent more time with these students, was more encouraging, offered more examples, and if she tried an example and it didn't work, well, these are the bright students, she said, I ought to be able to get through, and she found a way to reach them. The other side of the class, she taught them, she went through her lesson plan, she did her job, but she didn't spend as much time with them, was not as encouraging, and well, if she gave an explanation they didn't get it, well, they're stupid anyhow, what are you going to do? And she never got through. Now, can you see how this could really screw up your research? And so, what's the solution? Since this experiment expectancy can greatly distort the results you get, what's our solution to the experiment expectancy problem? Well, it's listed on the slide before you. Double-blind design. If the research subjects don't know if they're treatment or control, and if the experimenter, crucially, doesn't know who's treatment or control, then subjects can't act differently based on that knowledge, and the researcher can't treat them different based on that knowledge. The solution to experiment expectancy is to have a double-blind design. And understand what I'm trying to get you to do here. I know some of these terms you've seen before, but it's the pairing that's going to get you through the exam question. It's double-blind design to solve the experimenter expectancy bias. Lead time bias is next. In order to understand lead time bias, I have to take you out of the realm of experimental research to the, well, benefits, or how we try to estimate the benefits of early detection and screening. The problem here is that we think we've done good, we think we have good benefit of screening, when frankly we really haven't. And the best way to do this, I think, is concretely. You have before you 3 scenarios. A is the baseline. The patient gets the disease at 0, they're diagnosed, go up the timeline to at DX, and then they die when it says death, 5 years after the diagnosis. Okay, that's the baseline we're starting with. And now, scenario B. The patient gets the disease the same place they always did, but now, because of an early detection screening program, they're diagnosed substantially earlier than they were before. Of course, they die the same place they always died, right? But you'll notice, they're living 8 years after diagnosis, when before they only lived 5 years after diagnosis. Well, the problem is right there. There's a metric we love to use as physicians. How long the patient lives after diagnosis. See, used to be, I would say, patients only live 5 years after diagnosis. But now, with the new advanced screening program, they're living 8 years after diagnosis. See how much good we've done? Yeah, look again, we've done no good at all. Because the patients aren't living longer, we simply found out sooner. The death occurs at the exact same time. What's good benefit of screening? Scenario C shows you what benefit would be. The patient gets the disease at 0. They're diagnosed earlier, but now you'll notice they die later than they otherwise would have. In this case, 3 additional years after the baseline we started with. So, what is lead time bias? Easy. Lead time bias is confusing early detection with increased survival. It's confusing what we call front-end detection with increased back-end survival. What's the solution to lead time bias? This is fairly straightforward. Never use the metric of how long the patient lives after diagnosis. Stop it. It's fraught with confusion. Toss it aside, never use it again. What should you use instead? Life expectancy. Look at the scenarios presented. Used to be, scenario A and B, patients lived until they were roughly 77 years of age. Now, with the new advanced screening program, scenario C, patients live until they're 80 years of age. Measuring what we should measure. Not how much longer they're living after diagnosis, but how much longer they're actually living. 80 now instead of 77 then. Recall bias is next up, and recall bias is fairly straightforward. You're asking people to tell you about things that happened in the past, and, well, what they tell you is simply inaccurate. Now, this can be for a variety of reasons. Sometimes people lie, but that's not really what we're concerned about here. We're concerned about people that are saying what they think is the truth, but it's not. See, if you're trying to have people tell you about things that happened in the past, well, we all recode our past as we remember to be consistent with our present. And so, even though people are answering you honestly what they believe, they may simply be giving you false information. Let's be concrete. I want you to think back to when you were roughly 13 years of age. Remember back when you're 13? Remember the kind of things you thought about, the kind of activities you engaged in, kind of things that were in your day? All right, I'll answer that for you. No, you don't. Because what you tell me today about being 13, and what you'd have told me when you were 13, I guarantee you, two very different things. And if I was trying to understand being 13 based on what you told me today, I'd have a greatly distorted, that is, biased picture of what that'd be like. Second, when authority figures such as physicians ask questions, people usually feel like they should have an answer. And so if they don't have an answer, they just make crap up. So if you ask a patient for information, they come up with some information. But wait, it's worse than that, because then they say to themselves, well, that's what I told the doctor. I wouldn't lie to the doctor, so what I said must have been true. And in some very real sense, even though what they've said is absolute fiction, they come to believe it as absolute fact. Recall bias is a problem all through medicine, and it's certainly a problem for research. We tell you when doing an initial history and physical, just hearing what the patient has to say is often not enough. Checking with family is often part of how we're going to deal with the information the patient doesn't have. And that gives you a hint as to our solution here. The solution to recall bias is two words: confirmation, or another word you might see, triangulation. In short, check with different sources independently and see if you get the same information. So suppose I wanted to have a sense of what somebody had for, I don't know, lunch back in January. I say to somebody, what do you have for lunch January the 13th? The person thinks, I don't know, but I have to tell the doctor something. So he says, I had a bacon, lettuce, and tomato sandwich. Well, that could be pure fiction, but the person's going to believe it because they told me. And the only way I should feel comfortable with what that person said is if I get some independent confirmation. Let's say this person usually has lunch with a friend. I talk to the friend without that person in the room. I say, what do you have for lunch back in January? And the person tells me a bacon, lettuce, and tomato sandwich. Now I have much higher confidence about that information that I've gotten. Confirmation or triangulation. The bottom line here is recalled information must be confirmed. Without that confirmation, it's highly questionable just because of the way our mind holds on to and remembers reality. Late look bias. Late look bias is a problem when we're trying to get a sense of, characterize perhaps, a severe, maybe life-threatening disease. The problem here is fairly straightforward. The most severe cases of disease are least likely to be available to us. I won't be able to see the severe cases. They'll already be gone. I've looked too late. They're no longer available. Concretely, I've been traveling around the United States, indeed around the world, trying to get a sense of the symptoms of HIV and AIDS. To do this, I've been interviewing every AIDS patient I can find that would consent to be interviewed. When I've completed this exhaustive survey and I look at my data, I discover, much to my surprise, that the symptoms of AIDS are frankly relatively mild and not all that debilitating. Well, you know why I'd come up with those conclusions? Because the most severe cases will be, one, either dead or so demented that I simply can't extract any information from them. In short, I'm going to be biased towards the healthier, least sick, least disabled end of the spectrum. What's the solution to late look bias? The technical phrase we use is stratify by disease severity. And all that means is I shouldn't just talk to AIDS patients in general. We talk about 5 stages of HIV/AIDS. I need to make sure I have representation across the natural history of the disease. By stratifying according to classifications of severity, I can make sure I've represented each of those stages, that is each level of severity, so I haven't lost those most severe cases. We used to try to study suicide by talking to people that were suicide survivors, and we've discovered now that's a really stupid idea. Because the people that are suicide completers, people who go in and kill themselves, are very different people in temperament, profile, etc., than the people that are suicide attempters. Trying to understand who's available, the survivors, to get a sense of people that actually kill themselves is a bad idea. It's a late look bias problem. Confounding. Confounding means found within. Things wrapped up together so it's difficult to pull them apart. In a well-designed and well-run research study, there should be one and only one difference between the treatment and the comparison group, namely treatment versus non-treatment. Everything else should be the same. If everything else is indeed the same except for the treatment, well, that lets us apply simple logic. Since all was the same at the beginning except that one thing, treatment versus non-treatment, then any difference I see as an outcome at the end of the study must, of course, be due to that one difference I started with. But what if there's more than one difference at the outset? What if there's 2, 3, 4, 5, 6 differences? Well, then the outcome I find could be due to any one of those different differences, or indeed the combined weight of all of them together. The key issue: confounding is not an argument about what results you got. The results you have are clear. It's an argument about why you got the results. It's an argument about what's the cause, what's the interpretation of what made what's observed happen. Now, here's the bottom line, unfortunately. Every study is confounded. Sorry, but it's just true. I don't care if it's the lead article in New England Journal this month, it's confounded. Most research studies, at the start of the discussion section, have an area called limitations, which is where the researchers who conducted the research are telling you the confounding things they've thought about going forward. The idea here is to confess your sins before somebody else criticizes you for them. Every study is confounded. No matter how much you try, something always is not controlled for, something is always not eliminated from a possible explanation. So if every study is confounded, what's the solution? How are we going to solve this confounding issue? Well, first, you're obligated to run as good a well-run, well-designed research study as you can. In short, you're supposed to try to minimize confounding as much as possible. But minimizing is not the same thing as eliminating, right? So the real solution comes in do multiple studies. Understand the logic here. If every study is confounded, but each in a separate way, well, then the combined weight of all the research should help me get a lens in which I can get a good picture of what reality is. Each study is confounded differently, so the combined area of the studies creates a shared picture of reality that I can see clearly by the combination. What's the solution to confounding bias? Do multiple studies. And so please notice meta-analysis would also be an acceptable answer here, because meta-analysis is a series of rules and techniques by which we take different research done by different people, different times, different setting, and combine them to get that single conclusion, that single p-value, a summary of all the p-values from all the other studies. What's the solution to confounding? Do multiple studies or meta-analysis. And one final kind of bias, design bias. Design bias: the pieces of my study are not put together in a way that allows the right comparison to answer the question I'm trying to answer. The most common kind of problem